So this was not a lecture, but a workshop I gave at the hospitalist and the resuscitationist, and what I tried to do is take basic respiratory physiology, apply it to the ventilator, and then walk through some cases. I had about 30 cases prepared, and we'll go through a few here in this talk. So starting off with the basic mechanics of respiration, what we have here on the x-axis is pressure. This is atmospheric pressure. Everything to the left is below atmospheric pressure. Everything to the right is above atmospheric pressure. And then on the y-axis we have volume, and for this particular view it's displayed as percent of the lung's vital capacity. Now if I had a lung that was totally collapsed and I put it in a bell jar and I had the trachea exposed to the atmosphere, and then I started evacuating air from the bell jar around the lung, the volume of the lung would increase, and it would increase according to the slope of its compliance curve, such that the change in volume with respect to the change in pressure defines the compliance curve of the lung. And it would look something like this. Now you could do exactly the same thing for the chest wall. It's a bit strange, but you could take a lungless chest wall and you can see that at atmospheric pressure the volume is actually much higher than the collapsed lung at atmospheric pressure. To get the chest wall to decrease in volume on the y-axis, you actually have to lower the pressure inside of this lungless chest wall relative to atmosphere. So you'd essentially have to suck air out of the chest wall and it would shrink, and it would store elastic outward recoil pressure as the volume falls. And then above its equilibrium volume you'd have to increase pressure within the chest wall relative to atmosphere to continue to increase its volume. In any case, the chest wall has a higher equilibrium volume than the lungs, and the point at which they meet is the functional residual capacity, and it's slightly negative. It's a slightly negative pressure, that is, it's slightly below atmospheric pressure. So what happens when you take a breath in as you're sitting or standing and you take a tidal breath in? Well, this curve represents the compliance of the chest wall in its relaxed state, almost its paralyzed state. But that's not how the chest wall behaves. As we all know, the muscles of respiration contract and change the volume of the thorax. And what happens is it sort of has a physiology similar to the left ventricle in that it has time-varying elastance. The left ventricle varies from the end diastolic pressure-volume relationship to the end systolic pressure-volume relationship. But there's a whole bunch of different elastances between those two extremes. And the chest wall is somewhat similar. So when you activate the muscles of respiration, the chest wall behaves somewhat like this, in that it moves leftward and it increases the volume of the lung along the y-axis here. So you can see that at any given point in time, in order to increase the volume from FRC to here, the chest wall had to move from its relaxing state here to its semi-contracted state here, and this arrow here represents the pressure that the muscles of inspiration must generate to reach this volume, and similarly for here, and similarly for here at end inspiration. So this is the pressure of the muscles to change the volume. And so we can see part of the equation of motion is the total pressure at a given point in time invested into the respiratory system is partly defined by the change in volume divided by the compliance of the respiratory system. Now you could sort of intuitively, or maybe less intuitively, see that the compliance of the respiratory system is essentially defined by the area between the chest wall curve and the lung compliance curve, the chest wall compliance curve and the lung compliance curve. To the extent that one or both of the chest wall or the lung compliance curves splay downwards, down and to the right for the chest wall, down and to the left for the lung, and the area or the arrow between the two increases, that means that the compliance is decreased. So as an example, imagine the lung compliance gets worse. So the lung compliance shifts down and to the left. Now you can see the chest wall, to get to the same volume, now actually has to generate a larger muscular pressure. So you can see like that. In order to achieve each of these volumes, the pressure generated by the muscles is greater. So for the same volume as the starting situation, the muscular pressure is greater. Therefore, if this is the same, this is greater, we know that the compliance must have decreased. You could make a similar thought experiment for a stiffened chest wall. Let's say it's shifted down and to the right a bit. Well, the muscles of respiration would have to make up for that, and therefore to get to this volume or this volume or this volume, the chest wall would have to lift a greater distance. Thus the PMUS is greater, the input pressure is greater, the volume on the y-axis has stayed essentially the same, therefore the compliance is decreased. So you can see that a decrease in the lung compliance, in the chest wall compliance, or both, increases the amount of pressure required to generate a certain volume. So let's go back to our baseline situation at end inspiration. Now if you wanted to create the exact same volume, but not have the muscles of respiration do it, but instead a ventilator do it, now you have to apply exactly the same amount of pressure, but it has to be above atmospheric pressure. So you can see here, at this volume, the same amount of pressure is administered, but above atmospheric pressure to the lungs and the chest wall. So it's essentially just a mirror image of the muscles of respiration, but it's above atmospheric pressure. And a compliance curve is generated in light blue here. So this is the pressure that the ventilator is applied, assuming that the muscles of respiration are paralyzed here. And the astute observer might see that the change in pressure on the x-axis here is actually the driving pressure. Here the patient would be on a PEEP of 0, and this would be the plateau pressure, and that would define the driving pressure. And you can see how it flows from the area between the chest wall and the pulmonary compliance curve. So going back to baseline. Now when the chest wall contracts to increase lung volume, it's not just this muscular pressure in blue that drives the change in volume, but there's an additional component that is required to drive gas flow. So this is essentially a static pressure which speaks only to volume, but there's also an additional amount of pressure that's required to move tissues over each other. So when the inspiration occurs, there's actually this additional pressure that is proportional to the flow and the resistance of the system. And here this rounds out the equation of motion, so it's the elastic pressure, which is the tidal volume divided by the respiratory system compliance, plus the flow, V dot is just the first derivative with respect to time of volume, multiplied by the resistance of the respiratory system. So at any given point in time, the total pressure is a combination of these two subtypes of pressure. Now, the reflection on the ventilator is exactly the same. It's just reflected again. This is in a passive patient on the ventilator, not making any muscular efforts, but to see that the resistive components, the flow resistive components of the pressure also applies on the ventilator. It's just applied above atmospheric pressure. So if we were to turn this, if we were to move from what's happening during spontaneous ventilation to what's occurring in the passive or paralyzed patient on the ventilator, but turn this into a waveform graphic with which we might all be more familiar, we would move pressure to the y-axis and we'd move volume or time to the x-axis, and volume and time can be used interchangeably when it is constant flow or square wave delivery flow, because the same amount of volume is being administered per unit time, so time and volume become linear analogs. And so now if we just sort of flip this around and put it on this new graphic and add a little bit of PEEP this time instead of at atmospheric pressure, you can see that the The static or elastic pressure that's required as the breath progresses can be illustrated there with the compliance curve of the respiratory system in blue and the two red dots marking the driving pressure. And on top of that, the dynamic or flow resistive portion of pressure is depicted. So if you were to do an end inspiratory hold on this patient, you would then see that this is the peak pressure and this is the plateau pressure, which is essentially just divvying out the different parts of pressure from the equation of motion. When there's an end inspiratory hold, flow is 0, and therefore this portion becomes 0, and all the pressure is then related to the elastic portion, which we saw is directly related to the compliance or the distance between the area between the chest wall and lung compliance curves. So that was two examples kind of moving in parallel. One over here being spontaneous respiration without any assistance, and two, this being the equivalent ventilator-delivered breath in the patient that is essentially paralyzed. So that might help us think a little bit more clearly about independent versus dependent variables in the equation of motion. So we saw that the total pressure at any given time in the system is the elastic portion, which is the tidal volume over the respiratory system compliance, plus the dynamic portion, which is the flow times resistance. So we saw that the pressure generated by the muscles of respiration is thus equal to these two pressure subtypes in the patients that is breathing spontaneously. So when you're breathing on your own, the question is, what is the independent variable? That is the variable that's being changed, and what is the dependent variable? That's the variable or variables that are following suit. So when you're standing around breathing on your own, the independent variable is actually the muscle pressure generated by the muscles of respiration. And the tidal volume and the flow are linked. You can think of them as married, and that's why I've listed it as V dot here. So you link the V's together. The V dot is just the first derivative with respect to time. So if you know flow, you know volume, because you know flow over time. They run hand in hand. So these are the things that follow suit. So when you're breathing spontaneously, your brain is responding to local stimuli in the lung, demand from the tissues, pH, carbon dioxide tension, and it's using all of that and as well as the amount of volume the thorax is feeling and the amount of flow the thorax is feeling, and it's integrating that in the brainstem and then giving signals to the muscles of respiration. So these are changed independently, and these guys follow suit when you're breathing on your own. So we mentioned that this is the elastic component, this is the resistive component. When you add a ventilator into the mix, it gets a little bit more complicated. So again, it's the total pressure, and it's total pressure in the system at any given point in time is the summation of these two. And so the total pressure is the summation of the vent and the muscles working in tandem. What we saw in the previous slide with the chest wall and pulmonary compliance curve was on the left-hand side, only the muscles of inspiration were working to drive ventilation, and then on the right side, only the pressure generated by the ventilator was working. So that was sort of like a situation where the muscles of respiration were paralyzed, where only the ventilator was supplying the pressure to drive ventilation. Now in this situation, say when a patient is paralyzed, what are the independent and dependent variables? Well, unlike breathing on one's own, where the independent variables is the PMUS, the clinician can actually decide. So you kind of have two general selections when it comes to the independent variables. So you can either target or pre-select flow and therefore volume, because remember they're handcuffed together, as you would see in volume-targeted breath types as in volume assist control, or the clinician can make airway pressure the independent variable. Now, when one is the independent variable and the other is the dependent variable, so that's by definition the metric that will be changing on a breath-to-breath basis. So if you have flow and volume as independent variables, they will be the same for every breath, and therefore the pressure will change if there's any change in patient effort or respiratory mechanics. The converse is also true. If airway pressure is the independent variable, it will always be the same, and flow and therefore volume will vary on a breath-to-breath basis if there's change in patient effort or respiratory system mechanics. And so that's sort of the way you can go about interpreting ventilator waveforms, is looking to see which is staying stable and which variable is staying stable and which variable is changing, and then you'll know what are the independent and dependent variables. So when the muscles of respiration are active with the ventilator, then you can see effort in the tracings, and that can lead to asynchrony, which I'll touch on very briefly towards the end. So let's look at that situation where it's just the pressure generated by the ventilator, like in that first slide, just on the right-hand side. So when I look at waveforms, I almost always look at the flow first. So this is the flow waveform here. This is inspiratory flow, then there's a pause, and then there's expiratory flow. And when I look at the flow waveform, I almost always look at the expiratory flow waveform first, because I sort of see it as unadulterated. The inspiratory breaths are dependent upon the machine and what you've targeted. Is it a volume target? Is it pressure targeted, etc., etc. The expiratory flow is essentially just dependent upon the respiratory mechanics. So the ventilator isn't really driving any independent variables in expiratory flow. So here you can clearly see that there's severe obstruction, this sort of high flow and then rapid fall and flow with a kink sign, and then slow drawn out flow as gas escapes from obstructed airways, and then you can see that flow actually doesn't even get to zero before the next breath. So this is pretty bad obstructive airways disease. In the inspiratory flow, it's a square wave pattern. So this has to be volume control. Volume control always can only really have a square wave pattern. Pressure targeted breaths can't have a square wave pattern in order to maintain a constant pressure throughout the breath. And you know that from the equation of motion, because in pressure control, the pressure is rising throughout the breath as a function of the volume and compliance, which is going up. And therefore, if that's going up throughout the breath, the resistive component has to, or the dynamic component has to fall. So flow has to fall in order to maintain a constant pressure throughout. So therefore, because this is a square wave, we know that this is a volume control breath. And the area under this curve is volume. So this is flow, and the area under the volume time curve, the area under the flow time curve is volume. So you know the inspiratory volume, and similarly, the area under this curve is the expiratory volume. So we already knew this patient was obstructed just looking from the flow waveforms. And then when you do the inspiratory pause, this is confirmed here with a very large gradient between the peak and the plateau pressure. So that's quite different from this patient over here when you look at the inspiratory and expiratory flow curves. Here, there's an abrupt increase in flow, much greater than here, and then you have a nice mono-exponential decay curve emptying the gas. So the area under this curve is the expired volume, the area under this curve is the inspired volume. They should be essentially equal. In this situation, you can see that the peak pressure is a little bit high, but it's mostly driven by the plateau pressure. So this is a patient with poor elastic properties. That was the blue portion at the beginning. The plat is high relative to the peak, and as a clinical pearl, a lot of the times you can get a sense from that where the bend is in the pressure in volume control, where the pressure time curve bends, and you can see a small bend here, a small pressure at which the bend occurs. It usually correlates pretty well with with the resistive components here, or the drop from the P peak to the P plat. So again, these are patients where you only have P vent making a contribution. Similarly, we look at the flow. We see the area under the curve, it's square wave. We know this is a volume targeted breath. There's an obstructive expiratory pattern, and that's confirmed with the peak to plat ratio here. And here you can see the bend, where the pressure time curve starts to bend here, is great. So that again goes along with the high dynamic pressure component. So this is the same patient, but ventilated with a decelerating flow. So in volume targeted breaths, you can either have square wave or decelerating. As I mentioned, in pressure targeted, it's always decelerating. So you can change the flow profile to decelerating, but you can see in order to generate the same area under the curve, because flow is decelerating, the I time has to increase. And so you are when you're increasing the amount of time required to deliver the same volume because flow is decelerating, when you increase the I time, you actually decrease some E time. And in an obstructive patient like this, that could be problematic. They don't look like they've got auto PEEP here, but it's not a great strategy. And essentially all you're getting out of it is you're putting lipstick on a pig. You're making the peak pressures look a little bit better, but you could actually be harming respiratory mechanics in the long run by facilitating air trapping. So in patients with obstructive lung disease, a square wave pattern is more than adequate, and it gives you a better sense of what the true mechanics are, and it optimizes your E time. So this is a different mode of ventilation. So here we look at the flow, and the flows are all the same. The volume as the area under the curve is pretty comparable. Maybe there's a slight obstructive pattern here. So it's hard to know what the independent and dependent variables are here. But here the pressure is pretty flat. And the square wave or flat pressure coupled with the decelerating flow pattern strongly suggests that this is a pressure targeted mode of ventilation or pressure control. And in this situation, the pressure is the independent variable, and therefore the flow is the dependent variable, and that's the opposite of what we saw in the previous slides. So in this situation, it's the flow it's the deceleration in the flow that's telling you about the respiratory system mechanics. So a low resistance and a low compliance create a short time constant. So a short time constant creates a much greater slope, but it's much harder to extrapolate that data from the flow time curve and make sophisticated assessments about compliance versus resistance in patients on pressure control. So oftentimes you have to switch these patients over to volume control, make volume the independent variable, so then pressure becomes the dependent variable, and you can use pressure to determine the mechanics changes. So let's look at some waveforms with some muscular, some addition of some muscular pressure. So again, looking at the flow curve first, looking at the expiratory flow, you can see this sudden drop in flow. So this is the patient inspiring in, slowing down that expiratory flow, retarding expiratory flow. So this is a patient making inspiratory efforts. And you can see them slightly reflected in the pressure tracing here. But the flow will always be more sensitive because the change in pressure is related to the change in flow times the resistance, and the resistance in expiratory limb of ventilators is very low. So that means the pressure change often tends to be quite low because it's flow times resistance. So there's efforts going on here. It's a square wave, so you know it's a volume control, a volume targeted type breath. And there's a relatively high bend in the pressure time curve, so this patient may have some compliance problems, but we don't entirely know. Nevertheless, this is the dependent variable, this is the independent variable, this is what the clinician is controlling. So in this one, looking at the expiratory flow, again you can see a lot of effort. There's a decrease in flow, a decrease in flow, a decrease in flow. So this is the patient inspiring, retarding the movement of air. But during the inspiratory flow profiles, they're all constant. It's the same flow, the same flow, the same time, the same time. So you know that flow here, and therefore volume, is the independent variable. So the dependent variable is pressure. So this is a volume control mode. And you can see that the pressure is really scooped out here. And what that means is probably what's going on right here is the patient's continuing to have effort during inspiration. You just can't see it because the flow, it's an independent variable, but the dependent variable is picking it up. And so if you had a completely paralyzed breath and you map them on top of each other, the difference here is the P mus. This pressure is what the muscles of inspiration are doing. This is reflecting the effort that we're seeing during expiration and cryptically during inspiration. You can see before each breath there's this large drop in pressure. So there's just enormous amounts of effort going on here. And this patient probably has some degree of flow starvation, given the relatively low flow values that have been dialed into this ventilator. So similarly, looking at the flow waveforms, it's square wave. We know that it's a volume-targeted breath. The area under the inspiratory flow curve is the volume, and they're all the same. What's interesting here, though, is if you look at the expiratory flow, here you have this bend, right? And so it doesn't get that abrupt increase in flow followed by the mono-exponential decay. So this is a clue right here, and it's telling you that actually neural inspiratory time is probably outlasting mechanical inspiratory time, and so the patient here is actually inspiring, contracting the muscles of inspiration and inspiring beyond mechanical inspiration. It suggests that this patient too is having a lot of effort, but again, because flow and volume are the independent variables, you would not catch effort in the inspiratory time, in the inspiratory flow waveforms, but you do catch the effort in the pressure waveforms, because here pressure is the dependent variable. So this breath is paralyzed compared to these two. So if you were to lay this breath on top of each other, on top of these two breaths, you can see that this green area is what the muscles of inspiration are generating. So this patient is generating really strong diaphragmatic contractions that you can only see in the dependent variable waveform. You don't see it in the independent variable waveform because this is a volume-targeted breath. So moving on from this waveform analysis. So this is clearly a very different kind of patient with a different kind of mode of ventilation. And what is obvious here is that when you're looking at which variable is constant and which isn't, this one's a bit of a tricky one, but it's pretty clear to me that flow is the most variable. So therefore flow and therefore volume is the independent, flow and therefore volume is the dependent variable. And you can really tell because these flows are scooped out and quite variable, and that can really only occur when the flow and the volume are dependent upon the characteristics of the patient, the respiratory system mechanics and effort. And despite this large variability in the flow graphics, the pressure is pretty constant. So this looks like the independent variable. So this is almost certainly a pressure-targeted mode of ventilation. Now there's a bit of a curveball here, because here you can see the inspiratory time is constant, but this one is clearly shorter than all the others, but still appears to be a breath with pressure as the independent variable and flow and therefore volume as the dependent variable. And so what this probably is this is probably an SIMV pressure-targeted mode of ventilation with interspersed pressure support breaths. The expiratory flow graphic is pretty abnormal. It's almost certainly obstructed. there's tons of effort, there's ineffective triggering, so there's probably auto PEEP. Flow doesn't get back to 0 before the next breath starts, so this is a patient that's having a lot of problems with almost certainly underlying auto PEEP. And so just to bring home that point, this I time is very different from this I time. And so these are clearly dependent, clearly independent, but there's a bit of a curveball here because there's a different kind of pressure-targeted breath in here. That's pressure support. And again, pressure support is flow limited, while pressure control is time limited. So let's move on and talk a little bit about synchrony very, very briefly based on the discussion so far. So we sort of talked a little bit about it in that last patient. So again, what kind of form of ventilation is this? Well, I look at the flow first. I look at expiratory flow. There's an obstructive pattern. There's some effort, ineffective triggering most likely, and then flow doesn't get back to 0 before the next breath. So this almost certainly is auto PEEP in an obstructive patient. The inspiratory flow and volume is constant. So this is the flow and volume, is almost certainly the independent variable, making pressure the dependent variable. So in this situation, there's an end expiratory hold, and you can see that sure enough, there is extrinsic auto end expiratory pressure. So there's a threshold load on this patient for triggering the next breath, which is why there's so many ineffective efforts. And what's happened here is the patient has received a little bit of PEEP. So here the PEEP is essentially 0, and then you've dialed in some PEEP. The total amount of PEEP at the end of the breath is the same, but this increase in the extrinsic PEEP lowers that threshold load and should make it easier for the patient to trigger breaths. So this is an interesting waveform. So again, turning to the flow first, it's a square wave flow. So constant flow, constant volume means that this is the independent variable and this is the dependent variable, which could be confusing at first because if you just looked at pressure, this could be sort of confused as a square wave pressure waveform. It might make you think that this is the independent variable, but it clearly isn't. So then the question is, what's going on here? And you see this profound abnormality in early expiratory flow. Normally expiratory flow should be a sharp increase in flow and then a mono-exponential decay, but there's essentially no flow at the end of mechanical inspiration, and then you have this sort of slow, dragged out increase in expiratory flow, and this is almost certainly effort here. So neural inspiration is acting way longer than mechanical inspiration. So this patient has tons of effort, and I think that's probably what this scooped out pressure waveform is. I think if this person were paralyzed, it would be a nice kind of shark fin looking waveform, but because pressure is the dependent variable here, the muscles of inspiration are pulling the pressure down, which you don't see in the inspiratory flow because this is an independent variable. And then this profound effort that is occurring actually likely occurs again here, and the effort continues, but what happens because of this prolonged effort is they actually double trigger, and so they get a second breath. And so the volume here and the volume here, because volume and flow are independent variables, they stack, and you see as a consequence pressure, the dependent variable goes way up. And so this is a stacked breath. It's these two breaths going in quick succession. And then when you look at the expiratory flow, you see the area under this curve, or the volume, is very large. It's much larger than the expiratory volume here, and that's because it's releasing a double breath, and this certainly would violate small tidal volume ventilation. So if you see breath stacking like this from probably flow starvation or high respiratory demand, it certainly should be addressed. And that's it. A very quick run through on the basics of ventilation and how it could be very simply applied by analyzing flow waveforms and pressure waveforms on the ventilator. Thanks.